Section 300.13b of the 2023 National Electrical Code requires travelers and switch loops to be installed in multi-wire branch circuits. In a typical three-way switch circuit, two traveler wires are used. The travelers themselves are not mandated to carry the neutral conductor. However, it's considered a good design practice to include the neutral conductor with the travelers for several reasons. Firstly, ground fault protection. The neutral conductor offers a return path for fault currents. This enhances the effectiveness of ground fault circuit interrupters, GFCIs, and arc fault circuit interrupters, FCIs. Secondly, voltage drop mitigation. Including the neutral conductor alongside the travelers helps to minimize voltage drop, especially when dealing with extended cable runs. Thirdly, simplified troubleshooting. Having the neutral conductor readily available makes it easier to diagnose and resolve issues, such as open or miswired circuits. In general, running the neutral conductor with the travelers in a three-way switch circuit is advisable to promote safety, reliability, and ease of maintenance. Although it's not a mandatory code requirement, many electricians and engineers consider it a best practice. Therefore, while the code doesn't explicitly demand the presence of a neutral conductor with the travelers in a three-way switch setup, there are compelling reasons to incorporate it into the design. These reasons revolve around enhancing safety mechanisms, optimizing performance by reducing voltage drop, and streamlining the troubleshooting process. These considerations contribute to a more robust and user-friendly electrical installation. Let's delve deeper into each of these aspects to understand why this design choice is so widely recommended. Starting with ground fault protection, the presence of a neutral conductor ensures that any unintended current leakage can be quickly detected by GFCIs and FCIs. These devices are designed to trip the circuit when they sense an imbalance between the outgoing and returning current. Without a dedicated neutral path, the fault current might find alternative routes, potentially posing a shock hazard or even igniting a fire. By providing a reliable return path, the neutral conductor enables these protective devices to function as intended, swiftly interrupting the circuit and mitigating the risk of harm. Next, let's consider the impact of voltage drop. In long cable runs, the resistance of the wires can cause a significant reduction in voltage at the load end. This can lead to dimming lights, malfunctioning equipment, and overall inefficient operation. By including a neutral conductor, the current is more evenly distributed, reducing the load on each individual wire and minimizing voltage drop. This is especially important in larger homes or commercial buildings where circuits may span considerable distances. Furthermore, the presence of a neutral conductor greatly simplifies the troubleshooting process. When issues arise, such as a non-functioning light fixture or a malfunctioning switch, having a complete circuit with a neutral conductor allows for easy testing and diagnosis. Electricians can quickly verify the presence of voltage, check for continuity, and identify any breaks or shorts in the wiring. Without a neutral conductor, troubleshooting becomes more complex and time-consuming, potentially requiring the use of specialized equipment or the tracing of wires through walls and ceilings. In summary, while the National Electrical Code does not explicitly mandate the inclusion of a neutral conductor with the travelers in a three-way switch circuit, the benefits of doing so are undeniable. By enhancing ground fault protection, minimizing voltage drop, and simplifying troubleshooting, this design practice promotes safer, more reliable, and more user-friendly electrical installations. Therefore, it is strongly recommended that electricians and engineers incorporate this practice into their designs whenever possible. Now, let's explore some practical examples of how these principles apply in real-world scenarios. Imagine a situation where a homeowner is experiencing intermittent flickering of lights in a room controlled by a three-way switch. Without a neutral conductor present, the electrician might have to spend hours tracing the wiring, checking connections, and testing different components to identify the root cause of the problem. However, with a neutral conductor readily available, the electrician can quickly use a multimeter to measure the voltage at various points in the circuit, pinpointing the location of the fault within minutes. Another scenario might involve a commercial building with a long run of wiring between the switch and the controlled lighting. Without a neutral conductor, the voltage drop could be significant, resulting in dim lighting and unhappy tenants. By including a neutral conductor, the voltage drop is minimized, ensuring that the lights operate at their intended brightness and providing a more comfortable and productive environment. Furthermore, consider the case of a ground fault. If a wire becomes frayed or damaged, it could come into contact with a grounded metal surface, creating a path for current to flow outside of the intended circuit. Without a neutral conductor, this fault current might not be detected by the GFCI, potentially leading to a dangerous shock hazard. However, with a neutral conductor present, the GFCI would immediately sense the imbalance in current and trip the circuit, preventing any harm. In addition to these practical examples, it's important to consider the long-term benefits of incorporating a neutral conductor into a three-way switch circuit. Over time, wiring can deteriorate due to age, environmental factors, or improper installation. By having a complete circuit with a neutral conductor, the chances of developing problems such as open circuits, short circuits, or ground faults are reduced. This translates to lower maintenance costs, fewer disruptions, and a longer lifespan for the electrical system. Moreover, the presence of a neutral conductor can make it easier to upgrade or modify the circuit in the future. For example, if the homeowner decides to install smart switches or other advanced lighting controls, having a neutral conductor readily available can simplify the installation process and ensure compatibility with the new devices. In conclusion, the decision to include a neutral conductor with the travelers in a three-way switch circuit is a matter of weighing the potential benefits against the minimal additional cost and effort. While the National Electrical Code does not explicitly require it, the advantages in terms of safety, reliability, and ease of maintenance are undeniable. By incorporating this best practice into their designs, electricians and engineers can create electrical systems that are not only code compliant but also optimized for performance and longevity. Therefore, it is strongly recommended that the neutral conductor be included with the travelers in a three-way switch circuit whenever possible, as it represents a small investment that can yield significant returns in terms of safety, reliability, and user satisfaction. Now, let's shift our focus to the specific requirements outlined in Section 300.13b of the National Electrical Code, which addresses the installation of conductors in multi-wire branch circuits. This section states that the continuity of the grounded conductor, also known as the neutral conductor, shall not depend on device connections such as lamp holders, receptacles, and so forth, where the removal of such devices would interrupt the continuity. In other words, the neutral conductor must be installed in such a way that it remains continuous even if a device is removed or disconnected. This requirement is intended to prevent open neutral conditions, which can lead to dangerous voltage imbalances and equipment damage. When an open neutral occurs, the voltage on different branch circuits can fluctuate wildly, potentially causing appliances to overheat, motors to burn out, and sensitive electronic equipment to malfunction. By ensuring the continuity of the neutral conductor, Section 300.13b helps to mitigate these risks and protect both people and property. While this section does not specifically address the inclusion of a neutral conductor with the travelers in a three-way switch circuit, it underscores the importance of maintaining a continuous and reliable neutral path throughout the electrical system. This principle is directly relevant to the discussion of three-way switch circuits, as it highlights the potential dangers of interrupting the neutral conductor and the need to ensure that it remains intact even when switches are operated or devices are removed. In addition to Section 300.13b, other sections of the National Electrical Code may also be relevant to the installation of three-way switch circuits, depending on the specific application and the type of wiring method used. For example, Section 310.15 addresses the ampacity of conductors, which is the maximum current that a conductor can carry safely without overheating. This section provides tables and formulas for determining the appropriate wire size based on the expected load and the ambient temperature. When installing a three-way switch circuit, it is important to select conductors that are properly sized to handle the anticipated current, taking into account any directing factors that may apply. Another relevant section is 404.2c, which covers the installation of switches in grounded conductor circuits. This section prohibits the use of single-pole switches in grounded conductor circuits, unless the switch simultaneously opens all conductors of the circuit. This requirement is intended to prevent the switching of only the neutral conductor, which can create a hazardous condition. When installing a three-way switch circuit, it is important to ensure that the switches are properly rated and installed in accordance with Section 404.2c to avoid any potential safety hazards. Furthermore, Section 250 provides comprehensive requirements for grounding and bonding, which are essential for ensuring the safety of electrical systems. Grounding refers to the connection of electrical equipment to the earth, which provides a low impedance path for fault currents to flow back to the source. Bonding refers to the connection of metallic parts of the electrical system together, which creates an electrically continuous path that helps to minimize voltage differences and prevent shock hazards. When installing a three-way switch circuit, it is important to follow the grounding and bonding requirements outlined in Section 250 to ensure that the system is properly grounded and bonded, providing a safe and reliable path for fault currents. In summary, while Section 300.13b of the National Electrical Code is the most directly relevant section to the discussion of neutral conductors in multi-wire branch circuits, other sections may also apply depending on the specific details of the installation. It is important to consult the National Electrical Code and other relevant standards to ensure that all applicable requirements are met and that the electrical system is installed in a safe and code-compliant manner. Now let's address some common misconceptions and frequently asked questions related to neutral conductors in three-way switch circuits. One common misconception is that the neutral conductor is only needed for certain types of loads, such as electronic devices or appliances with sensitive circuitry. In reality, the neutral conductor is an essential part of any electrical circuit, regardless of the type of load being served. The neutral conductor provides a return path for current to flow back to the source, completing the circuit and allowing the load to operate. Without a neutral conductor, the circuit would be incomplete, and the load would not function. Another misconception is that the neutral conductor is only necessary for circuits that are protected by GFCIs or RFCIs. While it is true that the neutral conductor plays a crucial role in the operation of these protective devices, it is also important for circuits that are not protected by GFCIs or RFCIs. The neutral conductor provides a low impedance path for fault currents to flow back to the source, which helps to minimize voltage differences and prevent shock hazards, regardless of whether the circuit is protected by a GFCI or RFCI. A common question is whether it is permissible to share a neutral conductor between multiple branch circuits. In some cases, it is permissible to share a neutral conductor between multiple branch circuits, provided that certain conditions are met. The National Electrical Code allows for the sharing of a neutral conductor between two 120 volts branch circuits that originate from different phases of a 240 volts supply, provided that the load on each branch circuit is balanced and that the neutral conductor is sized appropriately to handle the combined current. However, it is generally not permissible to share a neutral conductor between more than two branch circuits, as this can lead to overloading of the neutral conductor and potential safety hazards. Another common question is whether it is necessary to run a separate grounding conductor with a three-way switch circuit. In most cases, it is necessary to run a separate grounding conductor with a three-way switch circuit, as the grounding conductor provides a path for fault currents to flow back to the source in the event of a ground fault. The grounding conductor is typically connected to the metal enclosures of electrical equipment, such as switches, outlets, and lighting fixtures, and it provides a low impedance path for fault currents to flow back to the source, tripping the circuit breaker or fuse and preventing shock hazards. In some limited cases, it may be permissible to rely on the metal conduit or cable armor as a grounding conductor, but this is subject to specific requirements outlined in the National Electrical Code and is generally not recommended. In conclusion, it is important to have a clear understanding of the role of the neutral conductor and the grounding conductor in electrical circuits, as well as the applicable requirements outlined in the National Electrical Code. By following these guidelines, electricians and engineers can ensure that electrical systems are installed in a safe and code-compliant manner, protecting both people and property.